National Electrical Code Section 240.12 addresses overcurrent protection. Specifically, Section 240.12b2 discusses a situation where the load is not continuous. This section dictates that the conductor serving the load shall be protected by an overcurrent device. This overcurrent device must be located no more than 25 feet or 7.62 meters from the point where the conductor receives its electrical supply. It is crucial to remember that this 25-foot rule applies to the load side of the transformer and not the line side. The overcurrent device, which could be a fuse or a circuit breaker, must be situated within 25 feet of the connection point between the transformer and the load it serves. The primary intention behind this rule is to offer backup protection for the conductor that serves the load. This backup protection is intended for situations where the overcurrent device and the transformer itself fails to operate correctly. There are situations where this rule does not apply. Specifically, the rule does not apply to continuous loads. Continuous loads are those that draw current continuously. Examples of continuous loads could include motors or large appliances that operate without interruption for extended periods. The 25-foot rule ensures that a fault on the load side is quickly cleared, minimizing potential damage to equipment and improving safety. Understanding this requirement is crucial for proper electrical installations involving transformers and non-continuous loads. When determining the placement of the overcurrent protection, begin by identifying the transformer's load side. Trace the conductors that connect the transformer to the load. The overcurrent device, such as a fuse or circuit breaker, must be placed along these conductors. Ensure the distance between the point where the conductor originates at the transformer and the location of the overcurrent device does not exceed 25 feet. This measurement should follow the actual path of the conductor, accounting for any bends or turns. Consider the type of load being served. If the load is continuous, meaning it operates for 3 hours or more, then the 25-foot rule might not apply. Consult the NEC for specific requirements regarding continuous loads. However, if the load is non-continuous, meaning it operates intermittently or for short periods, the 25-foot rule applies. Select an appropriate overcurrent device. The rating of the overcurrent device should be suitable for the ampacity of the conductors and the characteristics of the load. Refer to the NEC tables and guidelines for proper sizing of overcurrent devices. Ensure the overcurrent device is readily accessible. This allows for easy inspection, testing, and replacement if necessary. The overcurrent device should be installed in an enclosure that provides protection against environmental factors and accidental contact. The enclosure should be properly grounded to prevent electrical hazards. Before energizing the circuit, thoroughly inspect the installation to ensure compliance with all applicable codes and standards. Verify the overcurrent device is properly installed and functioning correctly. Use appropriate testing equipment to confirm the overcurrent device trips at its rated current. Maintain detailed records of the installation. This includes the location of the overcurrent device, its rating, and the date of installation. This information can be valuable for future maintenance and troubleshooting. Regularly inspect the overcurrent device and the conductors for any signs of damage or deterioration. Replace any damaged components immediately. If any changes are made to the electrical system, such as adding or removing loads, reassess the overcurrent protection to ensure it remains adequate. The 25-foot rule serves to protect the conductors feeding a non-continuous load from a transformer. The rule calls for the use of an overcurrent protection device located within 25 feet of the point where the conductors receive power from the transformer. The reason for this protection is to safeguard the conductors in the event of a short circuit or overload condition. This protection works whether or not the main overcurrent protection for the transformer fails to operate. Section 240.12b2 clarifies that the 25-foot rule applies specifically to non-continuous loads. It is very important to understand what constitutes a continuous load, which are loads expected to operate at their maximum current draw for 3 hours or more. Examples of continuous loads are lighting in commercial buildings or heating systems. Non-continuous loads include things like appliances that cycle on and off or machinery used intermittently. Section 240.12 outlines general requirements for overcurrent protection in electrical systems. It emphasizes the importance of protecting conductors and equipment from overcurrent conditions to prevent overheating, fire, and other hazards. The NEC specifies the types and ratings of overcurrent devices that are suitable for different applications. It also provides guidance on how to select and install these devices to ensure effective protection. Overcurrent devices are designed to interrupt the flow of current in a circuit when the current exceeds a predetermined value. This interruption prevents damage to conductors, equipment, and connected loads. Fuses and circuit breakers are two common types of overcurrent devices. Fuses are single-use devices that melt and break the circuit when an overcurrent occurs. Circuit breakers are reusable devices that trip and open the circuit when an overcurrent occurs. They can be reset and reused after the fault is cleared. The location of overcurrent devices is critical for effective protection. They should be placed at the point where conductors receive their supply to protect the entire length of the conductor. Overcurrent devices should also be readily accessible for inspection, testing, and maintenance. Regular inspection and testing of overcurrent devices is essential to ensure they are functioning properly. This includes verifying the device trips at its rated current and that it is in good condition. Damaged or malfunctioning overcurrent devices should be replaced immediately. Electrical systems should be designed and installed in accordance with the NEC and other applicable standards. This includes selecting appropriate overcurrent protection, installing conductors and equipment correctly, and grounding the system properly. Proper grounding is essential for preventing electrical shock hazards and ensuring the overcurrent devices function effectively. Training and education are essential for electrical workers to understand the principles of overcurrent protection and the requirements of the NEC. This includes training on how to select, install, and maintain overcurrent devices, as well as how to troubleshoot electrical problems. Continuous loads require careful consideration of overcurrent protection to prevent nuisance tripping. Nuisance tripping occurs when an overcurrent device trips unnecessarily due to temporary overloads or surges in current. To prevent nuisance tripping, it may be necessary to use overcurrent devices with high ratings or time delay characteristics. Coordination of overcurrent devices is also important in systems with multiple overcurrent devices in series. Coordination ensures that the overcurrent device closest to the fault trips first, minimizing the extent of the outage. The NEC provides guidance on how to coordinate overcurrent devices to achieve selective tripping. Overcurrent protection is an essential aspect of electrical safety. Proper overcurrent protection prevents electrical hazards, protects equipment, and ensures the reliable operation of electrical systems. The 25-foot tap rule, as it is often called, can be found in NEC section 240.21b. This section addresses the protection of tap conductors, which are conductors that are tapped from a larger feeder or branch circuit. The 25-foot tap rule allows for the protection of these tap conductors to be located further away from the tap point than would normally be allowed, provided certain conditions are met. Firstly, the tap conductor must not exceed 25 feet in length. Secondly, the ampacity of the tap conductor must be at least 1/3 of the overcurrent protection device protecting the feeder or branch circuit from which it is tapped. Thirdly, the tap conductor must terminate in a single overcurrent protection device that will protect the tap conductor from overload. Fourthly, the tap conductor must be installed in a raceway if it leaves the enclosure. These rules are to provide a degree of flexibility in electrical installations while maintaining a reasonable level of safety. Understanding the specific requirements of NEC section 240.21b is crucial for ensuring compliance with the electrical code and protecting electrical systems from overcurrent conditions. The concept of conductor ampacity is fundamental to electrical safety and the proper application of overcurrent protection. Conductor ampacity refers to the maximum current in amperes that a conductor can carry continuously under specific conditions of use without exceeding its temperature rating. Several factors influence the ampacity of a conductor, including the conductor material, size, insulation type, and installation method. Copper and aluminum are the most common conductor materials used in electrical wiring. Copper has a higher conductivity than aluminum, meaning it can carry more current for a given size. Conductor size is typically expressed in American wire gauge AWG or circular mils. Larger conductors have a greater cross-sectional area and therefore a higher ampacity. The insulation type of a conductor affects its temperature rating and therefore its ampacity. Common insulation types include THHN, THW, and NEC HHW, each with different temperature ratings and suitability for different applications. The insulation method of a conductor also affects its ampacity. Conductors installed in free air have a higher ampacity than conductors installed in raceways or cable trays due to better heat dissipation. The NEC provides tables that list the ampacities of various conductors under different conditions of use. These tables are essential for selecting the correct conductor size for a given load and ensuring that the conductor is adequately protected by an overcurrent device. When determining the ampacity of a conductor, it is important to consider the ambient temperature and any damping factors that may apply. Ambient temperature refers to the temperature of the surrounding environment. Higher ambient temperatures can reduce the ampacity of a conductor. Damping factors are applied when multiple conductors are bundled together or installed in close proximity to each other. These factors account for the increased heat generated by the conductors and reduce their ampacity accordingly. Overcurrent protection is essential for protecting conductors from overheating and potential fire hazards. The overcurrent device, such as a fuse or circuit breaker, should be sized to protect the conductor at its ampacity. The overcurrent device should trip and interrupt the flow of current before the conductor reaches its maximum temperature rating. When selecting an overcurrent device, it is important to consider the conductor ampacity, the load characteristics, and any applicable damping factors. The overcurrent device should be sized to protect the conductor but not so large that it allows excessive current to flow. Coordination of overcurrent devices is also important to ensure that the device closest to the fault trips first, minimizing the extent of the outage. Understanding conductor ampacity and the proper application of overcurrent protection is essential for electrical safety and the reliable operation of electrical systems. Always consult the NEC and other applicable standards for specific requirements and guidance. Proper electrical installation requires a thorough understanding of relevant codes and standards. It is always best to consult with a qualified electrician.